Good afternoon, everybody. This is another session of Everything I Forgot from Stats class. So today I will be presenting analysis of variance, and my name is Fadeke Ogunyake. So to give an overview of what I'll be talking about, I will touch on the background, the terminologies related to ANOVA, and ANOVA is analysis of variance, one way and two-way ANOVA, give some examples and show an example with SAS. So let's consider a situation where you're trying to buy a new product or testing a new technique, but you're not sure of which of the options is the best. It's a situation that is familiar to most of us. And your goal is to pick the best out of all the options you have. Bringing it to a clinical scenario or medical situation where you have 3 medical treatments to apply on patients with similar diseases. And one approach is to assume that the treatment which took the least time to cure the patient is the best among the 3 options. But the question is, what if some of these patients had already been partially cured, maybe by another medication, or something else is going on that you're not aware of? So how do you really determine which treatment option to go for? So that's where statistical analysis comes in when you have your data. And when you look at that chart, in the whole scheme of things, you're trying to figure out, are those medications, are they really different or are they the same? So a common approach to figure out a reliable treatment method would be to analyze the days it took the patient to be cured. And in order to make a confident and reliable decision about this or the options that you have, we need evidence to support our approach. And we can use a statistical technique, which can compare these 3 treatment samples and show us how different each sample is from the other one. So the technique, which I mentioned earlier on, that can be used to compare the samples on the basis of their mean is called analysis of variance, or ANOVA. And so just some background about ANOVA. ANOVA was developed by a statistician and evolutionary biologist, Ronald Fisher. The name was derived from the fact that in order to test for statistical significance between means, we are comparing or analyzing the variances between those samples or between the groups. So what is analysis of variance? This is a statistical technique that is used to check if the means of 2 or more groups are significantly different from each other. And what it does is it checks the impact of 1 or more factors by comparing the means of these different samples. So we can use ANOVA to either prove or disprove the scenario I mentioned earlier, if to determine if the medication treatments were, if there's a difference in the means or the time to recovery for those 3 medication different, if they were the same or if they were equal or not. So if we are comparing 2 means, ANOVA will produce the same result as t-test for independence or t-test for independent samples. However, when you use a t-test to compare more than 2 samples, it might not be reliable. And like I said, that's where ANOVA comes in, where you can have 3 or more samples. You can use analysis of variance to make an inference. So there are some terminologies related to ANOVA that is important that we understand, because that's kind of the behind the scene that happens when you're using statistical software like R or SAS or whichever analytical tool you're using, even Excel or whichever on SPSS. there are some things that are really happening that is important that we understand. So one of the terminology related to ANOVA is grand mean. This is mean is simple or arithmetic average. We all know that. But there are different means utilizing ANOVA calculations. And when you have the separate sample means mu, it could be mu1, mu2, or mu3, but the grand mean is the mean of sample means or the mean of all the observation combined, irrespective of the sample. So the grand mean is sometimes referred to as the mean of means. So that's a terminology that is important to know that's related to ANOVA. The other terminology is between group variability. You'll be hearing about between group variability and within group variability. So it's important to differentiate between those two. Between group variability, it refers to the variations between the distributions of individual groups. So you're looking at the group level as the values within each group are different. Each sample is looked at and the difference between the mean and the grand mean is calculated to calculate this variability. If the distributions overlap, and if you look at this, if it overlaps or if they are close, the grand mean will be similar to the individual means. But if they are far apart, the difference between the mean and the grand mean will be large. So how do we calculate between group variability? It's calculated in a similar way to standard deviation. So given that you have the sample mean and the grand mean, we can calculate the sum of squares for between group variability based on that formula. And what we do is that you subtract the grand mean from that group mean. Remember, this is between groups. This is not the individual samples. So when you have that, you square it, then we want to weigh each square deviation by the sample of the mean. So that's how the sum of square for the between group variability is calculated. So we find each square deviation, weigh them by their sample size, sum them up, and divide by the degree of freedom. Degree of freedom, we are very familiar with that terminology too. It represents how many values involved in a calculation have the freedom to vary. So for the between group variability, the degree of freedom is calculated by subtracting 1 from the number of sample means. From the number of sample means. That means from the number of the group means. For example, if you have 3 groups, you are subtracting 3 minus 1. So the degree of freedom will be 2. So after calculating the sum of squares of the between group variability, the next step to determine if there's a difference in the means or not is to find the mean square between those variability. And that's the formula that you use to calculate that. So just to have some kind of pictorial representation of the difference between groups and versus within groups. Between groups, you can see based on the picture. Let me use a pointer so that you know what I'm talking about. So when you look at the between groups, you have 2 different groups. And based on that, you can see one of the subjects is a different color versus the other one. But within groups, you are looking at a group, but you are looking at the individual sample or the individual observation within that group. I just wanted to bring this picture to kind of give you a clearer picture of what's between and within means, because it could be confusing. So the next terminology that is important in ANOVA calculation is referred to as within group variability. It refers to variations caused by differences within individual groups. Now you are not looking at group level, we are looking at individual observations, as not all the values within this group are the same. So each sample is looked at on its own, and variability between the individual's points is in the sample is now calculated. So you do that by measuring how much each value in this group differs from its respective sample mean. So let's look at this is just a formula to kind of bring it together for the sum of squares within. So here you have n as the sample size for that specific group, and the x bar I as the sample mean for group 1. But now you're subtracting the group mean from that individual mean. That's the J measurement from group 1. From that group, you're subtracting the group mean from that individual group. So after you've done that, you take the square deviation. I'm just bringing the formula together now. You take the square deviation of each value from its respective sample mean, you add them up, then you have the sum of squares for within group variability. Then you divide by the degree of freedom. The degree of freedom in this case is n minus k. And from there, you can have the mean square within group, the mean square of within the group variability. So this table or equation, some I refer to it, it brings everything together of the sum of squares. The total variability, that's SST, is the addition of SSB, that's between group variability, and within group variability. And if you look at each group, you see that for the between, you are subtracting the overall mean from the mean in each group. And if it doesn't matter if it's negative because you're going to square it. So at the end of the day, it's going to end up being positive. And for the within, you're subtracting that group mean from the individual value within that group. And that sums up to give SST the total variability. So the next terminology which we are all familiar with is hypothesis. It's an educated guess, like we all know about whatever we're thinking about around the world, but it should be testable either by experiment or observation. So you have the null hypothesis, which means that all the means are equal, or there's no difference between the means, and the alternative hypothesis, at least one population mean is different from one another. And this is as it pertains to analysis of variance. So the next terminology that is important is F statistic. This statistic, it measures if the means of different samples are significantly different or not, and it's also referred to as F ratio. When you have a lower F ratio, that means the more similar are the sample means. In that case, you do not reject the null hypothesis. And this, just the formula, is the between group variability divided by the within group variability. And the breakdown of that was what I explained earlier. So looking at this chart, you can see that the between group variance here is smaller than the within group variance. That means the numerator is smaller than the denominator. And in that case, when you have that, the F statistic will be smaller. So it reflects the likelihood of no significant difference between the three samples. This is just a chart to kind of bring it together and see how either larger or smaller value impacts the F statistic. And this F statistic, when it's calculated, is now compared with the F critical value for making a conclusion. When I talk about one of the examples I'm going to give, we'll see how that comparison is made. So in other words, bringing everything together, we have the mean square for treatment or between groups as the sum of square between groups divided by the degree of freedom between groups. And we have the mean square due to the error or due to the within the group as the sum of square within groups divided by the degree of freedom within groups. It's important to know that sometimes some of the terminologies can be used differently. Instead of saying between, you might have an example referring to it as the treatment group. And instead of saying within, you can have the example referring to as the mean square due to the error. So you have the total sum of squares as between sum of square and plus within sum of square. And the same thing is applicable to the degree of freedom. And this is just a formula to kind of bring everything together of what I've been talking about. So now we're going to move to the next thing about, now that we are familiar with some of those terminologies that is used in calculating the F statistic for analysis of variance or to determine the variance between variables, so independent and dependent variables, we will now go to the types of analysis of variance that could be done. I'm sure we must have heard about one way or two way. Is actually talking about, one way is talking about one independent variable. You can have two levels, but it's just one independent variable. For example, a brand of cereal. So the two level could be somebody having cereal, a particular brand of cereal, and no cereal at all. So the two way is you have two independent variables, and that could be multiple levels. For example, when the two independent variables could be brand of cereal and calories. And the brand of cereal, you can now have like multiple levels that are maybe Cheerios or other types of brands of cereal. So you can have them at different levels. So let's look a little bit more at one-way ANOVA. So giving some examples, which science department gives out lowest average grade? The explanatory variable in this case is the department or the independent variable, where the response variable is the student GPA for individual course. And another example is when you're trying to answer the question, which kind of promotional campaign leads to greatest store income? So the independent variable in this case will be the promotion type or the promotional campaign type, and the dependent variable will be the daily store income. So an example of a two-way ANOVA, how, supposing you have the question, how do the type of career and marital status? You can note there that there are two independent variables, type of career and marital status of a person relate to the total cost of annual claim he or she is likely to make on or his insurance. So the independent variables we have in that case of two-way ANOVA is you have the career, the type of career, and the marital status. Whereas the dependent variable is the health insurance payout. So before you can do analysis of variance, statistical tests, it's important to note that that like any other statistical test, there are some assumptions that are made, or if you are not sure if the assumptions are met, you might need to do additional tests to make sure that those assumptions are met. So some of the assumptions related to analysis of variance, especially the one way ANOVA, is that there are independent observations, and then normality, which you are familiar with, must come from a normally distributed population. And you want to assume that the variances are equal between treatments and that there's independence of errors and absence of outliers. In the event you have some outliers, there are some acceptable methods that you can use to either remove the outliers or to make sure that that's not a problem with that it will not impact the results of the variances. So if the assumptions hold, then under null hypothesis, F statistic follows F distribution with the degree of freedom between and the degree of freedom within for the sum of squares. So let's look at an example. Sometimes when you just talk about some of these terminologies, it might be confusing until you really look at a specific example. So suppose the National Transportation Safety Board wants to examine the safety of cars, type A, type B, and type C. And it now collects a sample of three for each of those treatments. So using this hypothetical data, we're trying to test whether mean pressure applied to the driver's head during a crash test is equal for those type of cars, for the three different type of cars. So for this, the first step is you state your null and alternative hypothesis. In ANOVA, the null hypothesis is the population means are equal, and as regards to this specific question we're trying to answer, the null hypothesis will be that the mean head pressure is equal across the three types of cars. And since in null hypothesis we assume that all means are equal, we could reject the null if one of the mean is different. That's where some of the inference comes in. But before we get to that, the alternative hypothesis would be that at least one mean pressure is not equal. So we now apply the appropriate test to either accept the null or to reject it. So having talked about all those components of the F statistic, the next step will be to try and calculate the F statistic by dividing the mean between groups by the mean within groups. So the total sum of square, if you break down based on the table I showed you earlier, if you do the mean within the groups, the mean, these are the groups, these are the between groups, the type A, type B, type C. And the individual value is now the within groups. So you want to calculate the total sum of squares for each of those. And based on that, we have the value, the mean value of the sample as 529, and the sum of square, the total sum of square as 96,303. So applying all those formulas I explained earlier too, you have the between or the treatment sum of square as 86,000 approximately, and the within or the error sum of square as 10,254. And then just a quick reminder, for the sum of square between, the group mean is subtracted from the grand mean. For the sum of square within, or the error, individual mean is subtracted from the within group mean. So the next step is to compute the mean squares, which you calculate by dividing degree of freedom by the sum of square, which gives us a value of 2037. And you can see we have 9 observations. The n was 9. So the degree of freedom to calculate the total mean square is 9 minus 1. So that's how we came about the 2000 value there. And then for the mean square treatment, or the mean square between, you have the value as 43,024. So the degree of freedom in this case is 3 minus 1 because you have 3 different groups: type 1, type 2, type A, type B, and type C cars. So that's why you have 3 minus 1. And here, for the within mean square, you are subtracting 9 minus 3 for the degree of freedom for the mean square error. So bringing it together, you have 1,709 for the mean square within. So now that we have all those values, we just slot it into the formula, and we have our test statistic as 25.17. So we now need to calculate the critical value. So to find critical value from the S distribution is required that we know the degree of freedom for the numerator, which is between, and the degree of freedom within, which we already know. So this table, I just took a snapshot of it to just have that particular section where we have the degree of freedom and the first degree of freedom on the horizontal, on the rows, and the degree of freedom on the column. So now to calculate the critical value, we at the alpha level. And don't forget, usually the alpha level is 5%, some go for 1%. So for this particular example, we are going with 5%, 0.05. So the degree of freedom 1 is 2, 3 minus 1. And the degree of freedom 2 is 6. So to calculate the critical value, we now look at the row degree of freedom, which is 2 in this case, and look at the second degree of freedom, which is 6. So our critical value is 5.14 approximately. So that's using the F table to calculate the degree of freedom, to calculate the critical value rather. So after that calculation, we now want to compare the F statistic, that's the observed, and the critical F value. And if it's greater, we reject the null hypothesis. And in this case, the F statistic that was calculated was 25.17, which is greater than 5.14. So we reject the null hypothesis at the alpha level of significance. That's at the 0.05 or at the 5% level of significance. So what's the interpretation? So we rejected null hypothesis and concluded the mean head pressure were not all the same for cars type A, cars type B, and cars type C. However, only one mean must be different to reject the null. We do not know which mean is or are different. And that's where this next step comes in. So this is the table that kind of summarizes all the results, all the calculations we've been doing. The sum of square within, the sum of square between, the sum of square within, the degree of freedom, the mean square, the observed, the F statistic, the critical value. And we also have the sum of square total and the total degree of freedom. So like I said, we know that one of the means is different, but we do not know which specific one. So there's some additional methods, or there are various methods for finding out which of the samples or for finding out which are the samples that represent two different populations, or to know the difference, which one specifically is different from the other. This Bonferroni approach, the leaves significance difference test, and the Tokis. Those are some of the methods that could be used. I'm not going to go into details about that. I have additional references that you could check at the end of the presentation to learn more about all the specific testing that could be done to know which specific mean, which one is different based on the grouping. So now let's look quickly at ANOVA with SAS. That's the statistical software I use for analysis most of the time, in addition to some other ones, but just to show us an example. So another question is that 3 reading instructions. This is the example I'm going to use with SAS. So 3 reading instructions were given to 15 subjects. Then a reading test is given where the number of words per minute is recorded for each subject. The question, therefore, is to test whether the 3 instructions, if they make any difference to the reading score. So you are trying to find out if there's any difference among instruction A, B, and C. And this is referred to as the global test. So this is the general SAS statement. Like we know, you could vary it. You could add additional options depending on the question you're trying to answer. That's why it's very important to understand the hypothesis so that you know which variable you are using as a class and which variable will be represented in the model. And you can try to find out the means of the dependent variable. So there are different variations of this ANOVA statement depending on additional questions that you have or what you are trying to find out from the study that you are working on. So before I explain these tables that were generated in SAS, I will go to SAS to just show us how it works there. And you can see the table generated there. Okay, just a minute to share the SAS screen. Can you see my screen now, the SAS output? Okay. So I've already imported the data into SAS, and that was it's just ideally you don't have this just few samples like this. It's usually more, and you have to do some backend cleaning and making sure that you either in SAS or Excel. But I just for illustration purposes for this presentation. So that's the data that was imported. So I have the SAS statement here. And running it now, and that is the result that was produced. So all the things I've been talking about since the formula, it was just a matter of just writing the statement and it just produced the results. And so the main thing about understanding those formula or those different terminologies, that when you now have the results, the interpretation will be meaningful to you because you know how exactly you set up the statement. So based on that, we have the procedure showing the class, which is the method, and then the levels. There are 3 different levels, A, B, and C. The number of observation read, 15, and the number of observation used, also 15. So you have I'm trying to get the pointer so that I can, doesn't seem to be responding. That's okay. So the dependent variable was words. That's the number of words based on the type of training or that was given. So you have the model, the degree of freedom to, it seems so easy when you just have those results together, but if you were doing it manually, you can imagine the amount of time it would take you to do all those calculations. So you have the model, you have the degree of freedom for error. You could also say that the degree of freedom for the between group, and that's 3 minus 1, that makes it 2. And the degree of freedom for the within group, if you put it in the context of how I explained the terminologies earlier. So you have the sum of square between as this, as the 215,000 thereabout, and the sum of square within as 77,080. And you also have the mean square calculated, and the mean square for the between, that's for the model, and the mean square for the error, that's for the within group. So we have the F value as 16.78, and the P value given was 0.003. So in this case, and the third table is just like based on the means method, we just try to find out the mean within a group and the standard deviation. That's an additional line that you can add. That, like I said, there are so many variations, there are so many options you can add to your statements. So I'll go back to the slides. So that's how you do it in SAS. And you can use R or SPSS or Excel when you use the analytics part 2, or whichever software you are familiar and comfortable with. So now we have the results generated. And this is what I explained earlier. The mean, we have it there for the different groups. And we also have the dependent, the procedure table for the different sum of squares, mean square, F value, all that just computed just by running the statement. So now to interpret the result. One way ANOVA is based on F distribution and the F test, and the statistic value that was given was 60.78 with a p-value that was 0.003. So since the p-value is less than 0.05, we reject the null hypothesis and conclude that the reading instruction methods were not all the same for the word count. So that's an interpretation of the results. And just to give a summary of what I've been talking about. So analysis of variance is a statistical method used to test two or more means. It provides statistical tests to determine whether population means of several groups are equal or not. The inferences about means are drawn by analyzing the variance, and it allows multiple groups to be compared at the same time to uncover the relationships between them. This was just like a basic type of analysis of variance that I described in this presentation. One way ANOVA, you could have two-way ANOVA, you could have like different levels, you could control, there could be a MANOVA where you have two dependent variables. So it could really get more advanced depending on the question you're trying to answer, the variables, and the model you're developing, and also depending on various things. But this is just the basic explanation of what goes on behind the scene for analysis of variance. And so those are my references, and some of them have links to the ad hoc test that you could do if you want to do the post test to really determine which specific group is different from the other. What we did was that there's a difference, but for further analysis, you could do additional tests to determine which of the groups is different or which of the means is different from the other. So that's all I have for analysis of variance, the basics about this. Are there questions or comments? Thank you for listening.